we'll start. The purpose of the first week is to get everyone on the same level, speeds, so that in the second week, each of you can focus on your data. In the beginning, we will be working with a couple of data sets that we have been using for a while, and that we have examples for, because you will see once you start applying code to your own data, you will all of a sudden bump into idiosyncrasies that is like, oh, it's not working. And before there are like 25 of us trying to figure out what 30 different problems are, we will try to go through these example data sets and have kind of a common narrative that we can all relate to. And before we do anything, I would like to take this opportunity to talk a little bit about movement data as such. So when we are actually working with movement data, we have collected movement data at some stage in our career, or we have been given movement data. And rarely I see people actually consciously think about what does it mean. What is movement data? How was it collected? And what does the way movement data has been collected or have been collected affect my choice of analytics and what I can do or cannot do with it? In general, we are distinguishing between two types of collecting movement data. One is a Eulerian method, and the other one is a Lagrangian method. Eulerian methods are like a video surveillance camera, or a camera trap, rings and bands, RFID tags, or microphone arrays. So camera traps are a good example. You put them on a tree, and you survey a certain area. And you will identify individuals who pass through this certain area. You might be able to identify these individuals. And you might have multiple cameras. And by kind of revisiting the individuals or resighting the individuals in the different cameras, you can deduce something that would equal to movement. It's kind of, if you have a fine enough grid of observation cameras, you probably can resolve the entire movement of an individually identifiable item. Leopard, cheetahs, whatnot. So everything that has dots or whales, for example, is a big source of data, movement data, because they have these chips in their fins. They can be individually identified. People go on whale watching tours. They send in the pictures. The pictures have a GPS, so we know, this whale was seen at this time over there. And then with the sequence of sightings, you can reconstruct the paths of animals. RFID tags. So if you ever have been in a place like London Tube, you can reconstruct your travel, because you check in and check out at every tube station, and with that people can reconstruct where you have been and which tube lines you have been using. So this is another way of collecting movement data in a Eulerian way. These bikes, the so-called Boris bikes in London, the same thing. You take a bike out of a bike stand with your phone app, then they know where your bike was taken, their bike was taken, and then you put it back into a bike stand somewhere else. And given that we know what the bike routes are in London, we can reconstruct movement. This is the Eulerian method. Most of us, as far as I can remember from the speed dating, have actually Lagrangian collected data, movement data. And that is, Lagrangian methods are the methods where we put a device on an animal, and this device is remaining with the animal and providing us continuous information, almost continuous information on its position. And because it is attached to an animal, it is equal to the position of the animal. RFID tags. Radio tracks, sorry. Satellite tracking, GPS, or geolocators. As anything that is attached to the animal and provides us positional information is the Lagrangian methods. The two methods differ in the ways what you can do from the data that you collect because of the uncertainty that is associated with it. So if you have a very low density camera trapping system, there is a lot of things the animal could have been doing. Your options are just way bigger than if you had a Lagrangian, like a radio collar on your animal. you would know where it is. And also in a radio color, we will see later that there is still some periods of uncertainty of what was my animal doing when I was not obtaining a position. But in general, we should distinguish between these two methods of collecting data. In general, if you are working with the Eulerian methods of tracking animals, you still need to translate that into something that is common with the Lagrangian method, which is position and time. So somehow you know what individual, where it was seen, and where and when it was seen. So the Eulerian methods in general pose a great challenge. It's not easy because we really need to translate between the spatial representation into something that is a movement representation. There is the assumption of unbiased sampling, but the devices are fixed and observation is happening in a certain place. Some cameras might not be able to detect individuals at night, or you might not be, I mean, although you can detect that there was an individual, you can't detect its individual identity. So they can be used. There's great examples, and increasingly people are trying to bring together these two fields, especially in camera traps and radio collars or GPS tracking. Sometimes we actually find animals that are sampled by both methods, by camera traps as well as with GPS. And the question is, of course, from an academic point of view, very interesting. What will happen if I actually analyze the data gained from a Eulerian method, the camera traps, versus from the Lagrangian method, the collars? And so far, the literature suggests that it depends. You will see different things, and they don't necessarily agree with each other. So if the device moves with the animal and records position in time, it in principle allows knowing where the animal is at any given time. That's the Lagrangian data. This is a data set that we will be using later. This is the buffaloes, Kruger buffaloes. So they had these collars, big buffaloes carrying collars. And technically, because we know where the collar is, and the collar is around the neck of the buffalo, we know where the buffalo is. So the different methods differ in mainly in their precision. And we already also see that there is probably error associated still with the GPS. Even though we have GPS on these buffaloes, there is this one odd point out there that suggests that maybe not everything is true about GPSs as much as we think or we would like them to be. So we will be climbing what is referred to as the ladder of lies. So we will be going through the methods that have been classically used in movement analysis, and many of them do not actually account for something that is inherent in all scientific data acquisition, and that's error. The error of the measurement. Every measurement is associated with an error, and this error of the measurement, of course, exists also in movement data. This is a VHF tracking study from around here. So this is Constance. And students have been tracking bats using VHF radio signals. And they have been triangulating them from two different places. They, of course, if you do the intersection of the triangulation, you will get the position. But if you add a 1 degree error, and this is pretty hard because you're kind of listening at the amplitude of the radio tracking signal, and then you're kind of pointing towards the loudest signal direction, and you can be 1 degree off. 1 degree is nothing, really. I mean, you're extremely precise. But if you do that in 1 degree, say, 1 degree in this direction, 1 degree in that direction, you will already get 5 degrees. 5 degrees, still very small. You will get an area of 18 hectares where this bat probably was. And that's only if you are within 5 degrees precision. So you will see that the different methods are associated with different amount of error. And this is actually the ideal situation because the intersection of these two stations is almost 90 degrees. That's when you have maximum precision. If you bring these two stations together, or if they are facing each other, 5 degrees will make a huge area, which actually might even go behind the second station. So this is something that we have to take into account. Our measurements are associated with error, yet most methods actually do not account for any type of error. What does that mean? Now, Another problem, and this is an imminent and big problem, and I'm not sure if every one of you is working on a database like MoveBank, but data standardization is a big challenge as well. As we are going into this new era of biological research, where we're getting more and more data, having the data in a standardized way is almost elemental to anything that we do later. Okay? Because I am still of this generation where people would give you data in Excel sheets, and you would spend, say, 90% of your time just to get the data into R, and then be certain that what you have in your computer is what actually represents what happened out there without having a stupid mistake. And this representation is, and making sure that nothing is wrong with the data and that you get the data that you're supposed to have, it hinges on data standardization. Hinges on agreement on coordinate systems, on times, but also in which ways we are representing the data. So if you use a system like MoveBank, then there has been put a lot of effort into data standardization so that the data are safe, they're standardized, so your script works with all your data sets. User defines privacy settings, so you know who sees your data. It has a simple visualization and so on and so forth. And you can access the data, which is on MoveBank, directly through R. So your code, your data is sitting on MoveBank, but your code can access the data that is on the database, and you know this is the format of the data. You know everything that you need. And in the end, should you publish your study, you can actually create a repository with the raw data and give it a digital object identifier, which allows you to cite your data source, but also others to reanalyze your data, to challenge you, because this is how we work scientifically. No one will be able to actually tag the exact same individuals, and the exact same individuals will not do the same things that they did when you track them. So in order to maintain falsifiability in science, we need to give access to the raw data. Otherwise, movement ecology will be just storytelling. I will tell you a story and you have to believe me. We don't want that. We want anyone to take our data and say, actually, I have a better method. Actually, I have another method. I think you made a mistake here. And for that, they need access to the data. And so with that, you can say, well, here's my data. Here's the DOI to my data. Go and challenge me. And then they will cite your data set, and they will challenge you. And this way, we all work together in order to learn something. It's not about me or you being right. It's about us learning something, which we truly can trust. So, the data sets that we will be working with. We will be working, depending on the context and suitability, with a few different data sets. These data sets are data that were collected by real biologists from real animals. It was work for them. They kindly offered us to use it for educational purposes. If you want to use the data sets, please make sure, as you would do in any other case, to get in touch with the data owners and involve them in your activities. So we have a bat data set, which I collected during my PhD. We have the African buffaloes from Wayne Getz. We have Leroy and Ricky, our two fishers. These are mustelids that Scott collected here at the Institute. They are part of the MOVE package. Leo the vulture, it's actually a she-vulture. So that is from Akopian Center for Raptors. So Sierit, the stork, in-house data set. And Habiba, an elephant data set. Value the elephant data set because elephant people are like raptor people. So whoever works with raptors knows what I'm saying. And so these data sets can all be found on MoveBank or are associated with the R packages Move and Move2. But you're, of course, free to use data sets that are made public. Do your research, but always please make sure that you get in touch because it's the way we treat each other in this community of data collectors and data analysts, that we work together and we give each other the opportunity. All of you who have collected data know it's expensive, it's hard. So you want that recognition as well because you share the data and you expect that people will also come to you and talk to you. Good. This already is it. I think we will straight jump in I'm looking at the more capable ladies. So we will jump into the data sets with loading them. I think you should all have them. Almost. I'll give you my microphone.
Some more definition. How does this work?
You just clip it to yourself.
Yeah.
And this somewhere else. Good. Are there any questions? Sorry. Does anyone have any question, remark? Want to join in the conversation?
I have a question.
Wait.
So,
Because we're
yeah. So just to clarify, how or why radio tracking data fits on the Lagrangian method if, for example, the tag is attached to the bird, but it doesn't record locations. You have to go and get it. Or, I don't know, automated radio telemetry stations, the bird needs to pass through them, right?
So, yeah, this is two different ways. So if we're talking about Motus, for example, that's Eulerian, because the antenna is recording, oh, there was a unit in my reception area. While when we are triangulating, two or more people at the same time are getting the direction, and from that direction we are determining the position of the device. We could do that every second if we wanted to. There are also automated radio tracking systems which, with circular antennas that are kind of triangulating continuously. That's determining the position of the device. Because the device is attached to an animal, we're determining the position of the animal. So it's not like we're surveying a volume of space and then saying, oh, an animal was here. We're actually asking the question, where is my animal?
Okay, so its location and presence absence is Eulerian.
Yes, exactly. So is someone here is different than where is tag number so-and-so.
With trucks, for example, classic truck survey, that's Eulerian method because it's presence absence. But if I can identify then the individual from the truck, then it becomes Lagrangian. Is that correct?
No, I would say both are Lagrangian. Okay. In one case, you do not assign identity, so it's a track. You could say, because you follow the track, you don't know which individual it is, but for the period of following it, your assumption it's an unknown individual.
Yeah, no,
So,
I mean,
yeah.
So no, I mean in case we are driving our road and then we are like a camera trap. I'm sampling a road, and then here is a leopard or here is a ostrich. That's Eulerian.
That would be Eulerian, but it's not on an individual. So because it's not on an individual, you would be like a presence-absence model, where you just say leopard, yes, no, yes, yes, and then lion,
But
wild dog.
I can identify the individual.
If you can identify the individual and you know something was here, and then later on the road, it came back here, you already know this individual was here. And then later at another time point, it was there. Or it walked back, and you can determine the time. So what you need for movement is position and time.
Yeah.
And then the entity for which you calculate position, it could be a collective. It could be my swarm. I saw my swarm, and it's composed of multiple individuals. I saw my swarm move like that. So then the entity is not an individual. Most of the time we're thinking about a single individual. So I know individual is identifiable, I can determine the position, and I can determine time or a sequence. It doesn't actually need to be absolute time. It can be first I saw it here, then I saw it there. And from that you will get movement. And we will also see what kind of minimum requirements are for movement data in R. It's pretty simple. I can already say it's position and it's time. If you do not have either information, you cannot talk about movement.